how do you go about making a nonlinear system? And this might be a biological system, it might be something else. How do you identify the variables, and how do you gather information, and how do you start creating a mathematical model?
So, first of all, if you think about a biological experiment, you don't have to make a nonlinear system, because most of the biological systems, in my opinion, are nonlinear. It just happens naturally. So if you're going to do an experiment on the cardiac rhythm, for example,
Mhm,
you start off with cells that are beating,
mhm,
or a whole animal or part of an animal that's periodic. The the basic properties of that system are that it's a nonlinear system. So
mhm,
from an experimental point of view, in doing work in biology, I don't think I think that it just happens naturally that you're going to be dealing with nonlinear systems.
mhm,
From a mathematical point of view, uh, the approach that we've always taken is we try to extract and think about uh, simple ways that one can represent the basic properties of that system, and write down the equations for those simple ways to represent the properties of the system. And most of the time, you're going to end up with a nonlinear equation.
mhm.
That's what happens with the equations for the genetic networks that I worked on with Stu Kaufman. Uh, Other people, a great applied mathematician named Balthasar van der Pol, was interested in electric circuits that could oscillate. And he made up an equation, which is a famous equation called the van der Pol oscillator, uh, which is a nonlinear equation. It was useful for describing systems that he was interested in electrical engineering to construct oscillators. But it's always also very, very similar to equations that people have proposed as simplified models for nerve cells and cardiac cells. So the basic properties of the basic equations that you might start thinking about when you start thinking about what's actually happening in the real systems and how can we represent these in simple ways, then people end up naturally with nonlinear equations. Just to elaborate a teeny bit more, one of the great pieces of work that's been done in applications of mathematics to physiology uh, were the Hodgkin-Huxley equations that were proposed back in 1952 to describe properties of squid giant
It's
axolotl.
the initiation of propagation of action potentials,
Yes,
right?
exactly. To action potentials and the ionic currents underlying those action potentials in squid giant axons. So beautiful work that was done in around 1950. Basic paper published in 1952 to describe the propagation of action potentials in nerve cells. Those equations are quite complicated. There are 4 different equations, I believe, and they're very nonlinear. They're very complicated. People tried to come up with a simplified version of those equations, and they did. They tried to get 2 different equations, dx dt and dy dt is equal to something on the right-hand side. And what turns out on the right-hand side is very similar to what van der Pol proposed way back in the 1930s. So those equations are called different things by different people, but
Yeah,
Fitzhugh-Nagumo
I go.
equation
Yeah.
is a nonlinear equation which has properties which to me, are amazingly similar to the properties that you can see when you do experiments on nerve cells